Hey everybody, we're going to be talking today about the curve of best fit. And so, in order to do that, we're going to start out with the line of best fit. Sometimes it's called linear regression. So, you may remember it from a little bit before, or if not, here we are. Let's go ahead and get that back into our memories. So, given data about x values and y values, we're going to go ahead and plot them on the graph. So, at 60, we're at 3.1, 61 matches with 3.6. 62 takes us to 3.8. 63 lines up with 4, and 65 is at this 4.1. Okay, so here is all of our points. And we're trying to figure out what the line for a best fit equation is there. So, thinking about this graph, right, where would a line go? Where would a line be represented to be the best representation of all of these points? The points might be on it, they might not, some above, some below, but we're going to try and figure out what is the equation of this pink line that I drew. And now remember, your line might be a little bit different than my line, and that's okay, but it's going to get us into the same ballpark. To get the same equation, though, we're going to use our graphing calculator for this. So here are all the directions that you need about how to put these in. Click our plus sign to add an item, and we're going to input a table. I'm going to use my x values from the table, put them all in exactly as we see them. And then I'll do the same with my Y values to type those in. And I always like to take my time and double check what I type in to make sure that I didn't make a silly mistake and my finger didn't bump the wrong button. So with these values in now, it's going to create the points on my graph, but I can't see them right now. My x's are in the 60s, but you can see that my x-axis is only going from -10 to +10 with that. So what I can do is use this magnifying glass in the margin. It'll zoom fit and it automatically adjusts the scale so that I can see these points on my graph. You can now see that my graph is focused from 60 to 65 in the x's, and that my y's are going, from 3 up to 4.5 to get those values in there. You can still zoom in or zoom out if you need to from them, but it gives you the idea. So we're going to go down to the next input line on our calculator and get it to write the best fit equation for us. So the formula that we're going to use is right here in the directions. Now, in our next input line, we're going to put in this y1 squiggle mx1 plus b. So it's very similar to y equals mx plus b, but the difference is that instead of y, I type y1 because that's the header on my table. Instead of equals, I use the squiggle or the tilde symbol if you take Spanish. And then instead of just x, I do x1 because that's in my table, and then the plus b. So the calculator knows when I type this in that I'm talking about a line. It creates that line on my graph so I have something to go with, something to grow from. So we're going to investigate a little bit more. You might need to scroll down. In the statistics section of that input line now, you have an R2 value. If this R2 value is close to 1, you have a really good representation. So 0.83, that's pretty close. A zero point 0.8 or a 0.9 in my R2 says that I have a great linear representation. If that R2 value is closer to 0, it's not doing such a good job to represent. My points are too far spread out. Then farther down in there, I get my parameters. It gives me an M value and a B value. Remember, M means slope, B means y-intercept. And so we're going to take those values, round them off to the nearest hundredths, and we'll use them to write the equation of the line. So we're going to have y equals my M value, 0.187. Well, that'll round my hundredths up to 0.19 for my M value. Then I do my X. Now for my B, it's a negative. So instead of plus B, I'm going to do minus, and this is going to be 7.96. So there you are. Here is the equation for our line of best fit. This is talking about having a y-intercept close to -8, and my slope is at this 0.19 value. So think about it as a rise 0.19 over a run of 1. That says it's not very steep for us. Now, follow-up question. What do we expect the y value to be if x is 72? So we're going to go ahead and plug into this equation, right? So y is equal to my 0.19 take out my x to replace it with 72 minus the 7.96. So I'm going to use this information. We're going to plug that in to our calculator. 0.19 times the 72 minus 7.96. So what is that y value? My y value is now going to be 5.72. So almost getting up there to 6. And does that make sense to you? Think about it. 72 is larger than any of the other x values that we have. And so as these y values were increasing, would I also expect the y to have increased that much? Seems possible. Now, number 4, on the other hand, asks us what do we expect the x value to be? It wants us to make a prediction about the x value if y is 2. So we're going to work this one a little bit backwards. It's going to be a nice equation for us here. So if y is equal to this 0.19x minus 7.96, and we're being told that my y value is 2, that's where we're going to replace. Take the y out, put 2 in its spot, and solve this equation. Think about those rules, right? How do you isolate the variable x? So I'm going to add my 7.96 to both sides. So that would be 9.96 equals 0.19x. And then I got to divide both sides by that coefficient. So 9.96 divided by 0.19. We're finding out that x then is about 52.42. And again, does that make sense? If my y value is 2, that's a lot lower on my table than anything else that I had. So my x value is probably also going to be lower than the 60 that I had. So you can use this best fit equation to make predictions about other things that are happening on the line. Now, this line of best fit only works if our data is linear, if it's following this straight line pattern for us. What if my data isn't linear, but it's more of a curve? That's where the back of our notes come in, and we're going to talk about the curve of best fit. Okay. So it's got a similar process to it as that line of best fit that did on the front, but we'll go through this. Table showing monthly sales in thousands for a new hair salon since the grand opening. So the steps for putting it into the graphing calculator are almost the same. We're going to insert a table with that plus sign and type in those x values like we see them. So my months, my time are going to be that independent variable. And then my y values are the dependent variable. Those are my sales that we're going to put in. Okay. And so when I put those in, you can see on the calculator, I hope that you notice these points are making a curve. They're tilting and curving up, not increasing at the same steady rate. So that's why we're talking about a curve of best fit, which is going to get us into the quadratic mindset. So after you have those points in, you can still use that zoom fit magnifying glass in the left margin if you need to adjust. I think I have a pretty good picture of what's going on there. So my next input line is going to be where I type my formula for the calculator. And here it is. It's similar to that pattern that we use for quadratics where we do the ax squared plus bx plus c. But again, instead of just x, we're going to call it x1 because that's what's at the top of our table. And we're making it into an equation, so we're talking about it being equal to y. And again, instead of equals, we use the squiggle. So y1 squiggle a x1 squared plus b x1 plus c, and it puts a line on our graph, or I should be more specific, it puts a curve on our graph. I'm going to hide this for just a moment so you can really see how that curve is happening. It falls through these points. Looks like a pretty good representation. So again, I can look at the R2 value that I have in my statistics. If R2 is close to 1.9995, really, really close to 1, and we would anticipate that. It looks like this line goes exactly through every one of those data points that we have. So seems visually like a good reference point, and statistically speaking, it has a good mention to it. So we're going to write the curve of best fit equation using that pattern ax squared plus bx plus c and replace these parameters a, b, and c that we have. Okay, so y equals my a value 0.12 x squared plus my b value 0.07 when I round that to the hundredths with my x, and then plus 5.59. Oops, but that would round up, so that's actually going to be 5.60 for it. Okay, so remember what we talked about with those features of quadratic graphs. The c value is supposed to be my y-intercept. So if I look at my y-axis, 0, 5.6, that lines up, and so the curve has my y-intercept at the right spot. My curve has a positive a value, which is why it's concave up. It's opening upwards. So those features still apply. They're still true to this curve. And we can also be so lucky as to still make predictions about sales or data based on what we have here. So predict the sales that this company has 12 months after opening. Well, the months are what we had typed in as our X values. So we're going to use that 12 to replace X. So we're going to think about this as 0.12 times, take the X out, put parentheses with a 12 in its spot squared, plus 0.07, take the x out, put 12 in its spot, and then plus the 5.60. You don't have to be able to do that arithmetic. We can ask the calculator to handle that for us. So 0.12 is multiplied by the 12 squared plus 0.07 times 12 plus 5.60. And here we are. The sales that we are going to predict for this company would be 23.72. Now, remember again, this was the sales given in thousands. So we're saying that this company might very well be making $23,000 after 12 months in sales. Okay, I'm going to go ahead and clear out this calculator so we can move on and try that example number 2. Mrs. Greaser's class did an experiment to roll a marble down different lengths of boards and timed how long it took. Here are the results. So I have to get this data into the calculator, plus sign to add a table, and my time is my independent variable, so that is my x value. And I like to take a moment, double check that I typed all of these incorrectly. Make sure that you've got the items X and Y lined up with their appropriate partners. There we are. And so I'm trying to plot the data. I can see a couple of points on my graph, but not all of them. So I'm going to go ahead and zoom fit to see more of these. And here's a curve happening for us again. Then we'll go ahead and write the quadratic curve of best fit. So that means that we go down to our next input line, use that formula again for the calculator. Instead of y equals, we do y1 squiggle. And now you start thinking your ax squared, so that's a x1 squared plus b x1 plus c, and we get the curve. Here it comes. So my R2 value, 0.9999, that's an excellent representation. This line fits the points very, very well. The points follow a quadratic pattern very, very well. Go ahead and plug these A, B, and C values into our quadratic equation then to fit that model. So y is equal to 0.51 for my A value that goes with the x squared, plus, oh, but my b value is a negative, so that's not a plus, that's going to be a minus 0.08 when I round there for my x, and then plus 0.04 as my c value. So there is the equation that we can use for our curve of best fit. Based on this, how long would it take for my marble to roll 15 centimeters? Well, 15 centimeters for us is the y value. So I want to look on my graph and find out where is that y equal to 15. So is it possible then for me to use this point at negative 5.3? That intersection gives me a negative time. We can't travel backwards in time. That doesn't happen. So I must be using the intersection then in my positive intersection. So that's around 5.5. So based on this equation, based on where my y value is going to be 15, this is going to be about 5.5 seconds. And lastly, number 4, approximately how far does our marble travel in 3 seconds? So 3 seconds is my time, that's my x. We can absolutely plug this in, 0.51 times the 3 squared minus 0.08 times the 3 plus 0.04. So we get to type that in. Oops. 3 squared minus the 0.08 times 3 plus 0.04. So how far is that marble going? About 4.39 centimeters would be the answer to that. You can also do this by that same approach that we used up above in the question number 3. Since I know that I'm talking about the 3 seconds as my x value, I want to ask where is x equal to 3? Find out where those lines intersect. When x is 3, my graph comes out with 4.37 compared to what we just did with the 4.39. Remember, there's going to be a little bit of rounding error going on with some of these, but we're definitely still talking about the same thing. I hope you're doing a lot better following along with how to find these curve of best fit equations.